And welcome to lesson 5. We'll be taking a look at Newton's second law. So you can see it actually, this would be the way that Sir Isaac Newton would have defined Newton's second law. He would have said acceleration is proportional, directly proportional to the net force acting on an object and inversely proportional to the mass. This is how he would have said it. I'm just going to write out those words for you. So the acceleration of an object is directly proportional to the net force acting on the object. There we go. And inversely proportional to the mass of the object. How could we show that graphically? Well, if we have a small mass versus here, if I have a small force, you could have a big mass with a large force. So here, the acceleration would be equal to this small force divided by a small mass. And here, the acceleration, there is a large force divided by a large mass. What I'm trying to show by that graphically is that here the acceleration of these two objects might actually be the same. Here, if I've got an object with less mass, and if I make the mass larger in the second object, that would cause the acceleration to decrease because it's inversely proportional. But if I also make the force larger, that would compensate for that, and you might actually have the same acceleration. Now I realize that I did the words part here, so here I'll use this part to define what each of these means. A is equal to acceleration, and that the units for that is meters per second squared, or you could say meters per second per second. The force, the net force, is equal to the sum of all the forces. Oops. Must have done something weird there. Fnet is equal to the sum of all the forces, and the units for that is newtons, and m is equal to the mass, and we measure that in kilograms. Okay, so let's try this here. If we fill in this chart, we can think that Fnet is equal to the mass times the acceleration. So we kind of set up the chart in a friendly way. So you can say, well, if the net force is 10 and the mass is 2, then this would have to be 5. Okay, now let's think here. From line 1 to line 2, what did we do? We multiplied the force times 2. Well, just looking at the words here, the force is directly proportional. So whatever I multiply the force by, that acceleration is also going to get multiplied. So from here to here, I'll go back to my pen. From here to here, oops, get this back. From here to here, I multiplied times 2. And I kept the mass the same. So in other words, the acceleration is going to get multiplied times 2. So I would get 10 there. Okay. What about from line 2 to 3? Here the force stays the same, but if I double the mass times 2, now the acceleration is inversely proportional to the mass. If I have more mass, the same amount of force is going to accelerate it less. So this is going to get it multiplied times the reciprocal of 2. Or another way of thinking of it is to say divide by 2. So that 10 is going to go back into 5. Okay. How about from line 3 to line 4? I think what force? Remember, force is equal to the mass times the acceleration. 2 times 5 is going to be equal to 10. 10 is equal to what times 10? 1. Okay, so you kind of have two ways of doing these questions. One, you can think of this formula here, and the other one is you can do this kind of proportional thinking if you've got two different lines. Let's try to check your understanding here. It says determine the accelerations that result when a 10 Newton force is applied to a 3 kilogram object and then to a 6 kilogram object. So I have my two versions of writing my formula. It turns out I think that this version is better for this question because it's solving for acceleration. So for my first object, I'm going to say the acceleration is going to be equal to 12 over 3, which is 4 meters per second squared. And for my second object, my acceleration is going to be equal to 12 over 6, which is equal to 2 meters per second squared. And you'll see, if you think proportionately now, I'm taking this mass, I'm doubling the mass, and because mass is inversely proportional to acceleration, you'll see that the acceleration got multiplied by a half or divided by 2. Second check for understanding. It says suppose that a sled is accelerating at a rate of 2 meters per second squared. I think that 2 should be superscript. If the net force is tripled and the mass is doubled. Okay, so let me think about this. If the net force is tripled, in other words, this force is going to get multiplied by 3, well, what will that cause as a change in the acceleration? Well, whatever the force is multiplied, this acceleration is also going to get multiplied by 3. And now it says the mass is doubled. Well, that's the same thing as saying times 2. And now since mass is in the denominator, or another way to say it, since the mass is inversely proportional to acceleration, now the acceleration is going to get multiplied by the reciprocal of 2, or 1/2. Okay, so in other words, this acceleration is going to get multiplied by, can I combine that together? 3 times a half is going to get multiplied by 3 over 2. The original acceleration was 2. So the answer is going to be 3 meters per second squared. Now this part here, you can think about how fractions are multiplied. You could say 2 times 3 is 6, and 6 divided by 2 is 3 again. I find it easier just to cancel out those 2's. Okay, hopefully that makes sense to you. Let's take a look at this next page here. If the downward force is the force of gravity, find the acceleration of the object. Well, if we have A is equal to Fnet over m, so first of all, Fnet is the sum of all those forces. So it seems to me that the top and the force upwards and the force downwards is canceling each other out. So really, I've got a net force of 20 newtons left. I am almost there, but now I need to know what the mass is. And they don't tell me what the mass is. Well, here's the hint. They tell me that the force of gravity is equal to 50 newtons, and I know that Fg is equal to m times g. Now we're going to keep things simple. Instead of using g equals 9.8, we're going to say it's approximately 10 in this case. So I'm going to say that if the force of gravity is 50, mass times 10, to solve for mass here, I divide both sides by 10, so the mass is going to be equal to 5 kilograms. So you see how that works. I use this information here to solve for mass. If the downward force is the force of gravity. Those are all the clues that led me to say that the mass has to be 5 kilograms. And now I'm ready to go back here and say, okay, my Fnet was 20 newtons left, divided by 5, and now I get 20 divided by 5 is 4. Now this acceleration is a vector, so it has a number, it has units, meters per second squared, and it has direction. Now whatever the direction is of the Fnet, that's going to be the direction of the acceleration. So that's the same, always the same. Whatever the direction is for the net force, that's going to be the direction for the acceleration. In fact, that's what we're talking about right here. It says, consider the 2 oil drops below for an acceleration of a car. From the diagram, determine the direction of the net force. Okay, so the car is moving to the right and it's speeding up. So the acceleration is to the right. So Fnet equals to the right. I don't know the number, I don't know the magnitude, but I know the directions to the right, because it was moving to the right and speeding up. You can imagine if I had to take an object and use my hand to push or pull it to cause that motion, I would be pushing it to the right. How about this one here? The object's moving to the right, but it's slowing down, so the acceleration is actually to the left. The Fnet would have to be to the left. It doesn't mean that there's only a force to the left. There could also be a force to the right, just not as great. Okay, if I had to add them all up, and there's probably a force of gravity and a normal force and all kind of stuff, where these two might cancel each other out. So you could see that kind of a free body diagram would indicate an Fnet to the left, and that would be an example for that car. All right, that's it. For the worksheet, you got page 12 to do, and Newton's laws, Minds on Physics, sub-level 7. I'll see you in class.